Okay, so we're doing this one here. So LT5, and let's see, we're doing part 3 here. So I'm in my own way. There we go. So you're right that this is not a linear transformation. And by the way, the visual tip-off, just before we get into the algebra, 0 doesn't go to 0. Right, you plug in x, y, z equals the origin, and what you get is 0, 0, 1. So we know that all linear transformations have to take the origin to the origin. This doesn't, therefore it's not a linear transformation. But now the problem says to use the definition. So I need to find some vectors that I could plug into the definition that would contradict what the definition says has to happen. So let's consider, I sort of know from my observation that 0 is really kind of the problem. Right? So I'm going to pick, let's look at 0 and 0. And let's ask the question, is h of 0 plus 0, is that equal to h of 0 plus h of 0? Well, let's see here. H of 0 plus 0, that's just h of, well, let's see, 0 plus 0 is 0.
Quick question.
Yeah.
You don't need 3 zeros?
Well, this is the vector 0, 0, and that's the vector 0, 0. I'm just using. I shouldn't.
You don't need one for 0? I guess
Yeah, like you don't need one for the z coordinate.
No, I'm sorry. This is I misspoke. This right here, this when I say 0 vector, that's 0, 0, 0, and so these are two separate vectors. Remember the rule that is required. You need h of x plus y to equal to h of x plus h of y. So this is my x, and this is my y that I'm choosing. Yeah, these aren't coordinates; these are vectors.
Okay.
Yeah.
And those vectors are 0, 0, 0.
Yes,
Okay.
that's right. Yeah, that's right. So yeah, 0, 0, 0. Indeed. Yeah.
It's going to be a 3 by 2 matrix. Because I thought that.
This is not a matrix at all. But this is just a linear transformation. This is a would-be linear transformation, which we're going to show actually is not a linear transformation.
I think I'm confused that why there's 3 vectors instead of 2. Because like you have an x.
There's 2 vectors.
Because like the definition states that it's x plus y vectors, 2 vectors, and
Yeah.
within those vectors it's the 3 x, y, z. So you just have to prove that the
Yeah.
x and the y vector.
This x right here has 3 coordinates. This y here has 3 coordinates. But there's only 2 vectors. Each one has 3 coordinates.
It's not x, y, z.
Yeah. So yeah, it is very confusing. That it's easy to, and I kind of talked about this during this section that you can use indices to distinguish different vectors from each other, or you can use indices to distinguish individual coordinates within a vector. So you always have to kind of be on the lookout for, wait a minute, the thing that I'm looking at, what type of object is that? Yeah. So anyway, I claim that h of 0 plus 0. Well, 0 plus 0 is 0, and h of 0, I can look at the function there and see that this is 0, 0, 1. Now let's compute this side, see what that is. Well, h of 0 is 0, 0, 1, and then h of 0 is 0, 0, 1, and that is 0, 0, 2. And these are not equal. Therefore, this didn't work. So the condition 1 is not satisfied.
A quick tag-on question.
Yeah.
So that took up like half a page. Mine took up like 2 pages.
Oh my. Yeah.
So with all that stuff with like doing the A, B, and C coefficients and stuff.
Yeah.
Is that just the longhand version of this?
No, that's a different thing. There we were proving that something was a linear transformation. And it's much harder to prove that something is true than to prove that it's not true. Right, so, for example, what if I wanted to prove that everyone on Duke campus has some property, and let's suppose momentarily it's a true fact that everyone on Duke campus has that certain property. I got to go talk to there's thousands of people on this campus, right? Now, let's suppose I wanted to prove that not everyone on this campus has that certain property. All I got to do is find one, right? Find any single solitary person that fails the condition, and I'm done. And it's just much easier very often. So here I've only found one counterexample to that condition. But that's all I needed. the condition failed to be always true, and therefore it's not always true, and therefore this is not a linear transformation.
If you were going through, like, let's say you thought it was linear transformation, like you just assumed it.
Yeah.
And you went through the whole process with ABC.
And that's what you did? You sort of tried to prove that it was, and the process failed?
So what my question is, I guess, about the failure.
Yeah.
So what I assumed was the failure was the addition of the 1, because it's like a 0, 0, 1 vector.
Yeah, that's right. The one, yeah. Mm-hmm.
And so once you see it's like, okay, there's proper form, but then all of a sudden there's a 0, 0, 1 vector tag on the end. That means it's failed. Is that?
Yeah, that's right. The point is that, this and this. So you computed this brute force. Well, you probably did ax plus by, I think that sounds like you said. And then you computed a h of x plus b h of y. And the two things, they ended up not being equal. Now, how they ended up not being equal, I think you said it ended up being that there was just like an extra 0, 0, 1 on the right.
Right.
Well, that's not equal. So, therefore, you're done. Yeah. Okay. Now, you're right. You did sort of more work than was necessary by showing that not only does this condition sometimes fail, but you showed that it usually fails. Yeah. In fact, maybe it always anyway, but it certainly usually fails. Okay. And that's just more than the problem needed you to do.
Yeah. So like unless you think of a counterexample off the top of your head, you have to go through that process then?
Yeah, but again, you really can cheat a lot with these because we know fast forward to the next section, we know all linear transformations have to look like matrices. And because that's what matrices are. And you can just see, well, that little plus 1, there's no way that plus 1 could come from a matrix times a vector. And so you instantly know it's not. And honestly, when something is not a linear transformation, most of the time you could just take a random guess and it will probably fail to satisfy this condition. Here are a couple of random vectors, x and y, will probably fail. Yeah. But if depending on the nature of the problem with the function, you might want to, try to make your guess to sort of key off of what that, if you can see what the problem is. And in this one, the problem, as we've talked about, the problem is that. And so you want to think about, how can I key off of that somehow or another? Yeah. Yeah.
Would you mind showing them, like, notation on, like,
how to do it the long way?
Yeah, like,
okay.
Five
sure. I'm sorry? How to do one that works? Yeah. Okay. Well, so
I just feel like I'm writing it wrong.
Okay. We did one that works. Back here in the section. That was this calc. Nope. Yeah, that was this thing here. So I showed that f of ax plus by was af of x plus bf of y, and I did that by saying, well, here's ax plus by. Let's write down explicit coordinates for x and y. Then here's ax plus by. And I can multiply that out and add them up. There you go.
But do you pick A and by? I mean, A and B?
So what you need this to always be true no matter what A, B, X, and Y are. So you got to leave them as variables.
Okay.
Yeah, if you're trying to show that something is always true, then you don't get to make choices. Right? And so we're currently trying to show that this is a linear transformation, namely that this is equal to this for all A, B, X, and Y. And so, yeah, we have to leave them as variables and show that the algebra forces that, which simplifies to that, which you can rewrite as that, which is actually equal to this. It just flat always works because of the algebra. Yeah. And, yeah, now I don't know about 2 pages. I don't know if it should have taken 2 pages. Maybe you write bigger than I do. Yeah, right. That's fine. And that's probably a good thing. I should probably write bigger, yeah.
Were we finished at number 5? Were we supposed to show the other condition? The example we just did?
The one we just did.
Yeah,
well, we don't have to in the one we just did because this function, where was it? Let's see, it was this one. This function failed to satisfy the first condition.
Oh, okay.
So we already know it's not going to satisfy both conditions because it failed the first one. So it doesn't matter. Even if it did satisfy the second condition, it wouldn't matter. Yeah.
Another question. You said you can visually tell if it's a linear transformation. So I'm going to use that theorem. So with number 4 and 5, you could just visually look on it before you even see it.
Yeah.
I'm going through the same brute force process too, so I'm still not
Well, okay. So here's how you know by casually telling, and that is that if you look at the next section here, all linear transformations. Remember, they're all can be entirely determinable by the images of the standard basis vectors, and so we can write them as matrices. So I claim all linear transformations have to look kind of like this kind of thing. In other words, the output components have to be nothing more than linear combinations of the input components. So you can't have any exponentials, nothing can get squared. You can't even have like a constant sitting over here, like a +1, +10, whatever. Nope, not allowed. Just terms like this. Constant times input variable. Constant times input variable. Constant times input. That's it, right? So that's what linear transformations look like. Now that's just an intuition. I mean, that's, it comes from this subsequent stuff. And back here in this problem, just between you and me, yeah, I know at a glance that this is not a linear transformation. But what I wanted you to do was to find explicit vectors that fail the conditions.
Oh, okay.
Yeah, and so I wanted you to, here you could plug in like, let x, x is a bad choice. Let A be the vector 1, 2, and let B be the vector 3, 4. You can just plug in and see it's not going to even come close to working. Yeah. 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 So notice, by the way, I did do one of these in the section here. So I did one of the easy ones here. So here we had to go through the whole calculation to show that it does work for this one because this is a linear transformation. But this one, remember we talked about this, we decided that doesn't look like a linear transformation because it's got a square there, and I just found a counterexample and walked away, right? So these exercises are really kind of a lot like this example here.
So for the one that you just did, like,
yeah,
so you don't even have to write all that junk out. You just say like, oh, it looks kind of fishy. And then
No. You do. It did say find explicit vectors. The problem asks you to like do something kind of like this, where you find explicit, vectors that this would have to equal to this if it was a linear transformation. They don't. Therefore, it's not a linear transformation. But you don't have to do the whole. You don't have to work out the whole long, tedious thing like it sounds like you did. Yeah. But yeah, I mean.
But you just pick a random vector.
Yeah, but pretty much. Yeah, it could be pretty much random. Because all you have to do is find any counterexample. And the good news is that things that are not linear transformations tend to be chock full of counterexamples. Yeah. Now, you might get unlucky and pick some vectors where it actually happens to satisfy the condition for those some vector. That does happen sometimes, but yeah. Right, but so this is all, for this problem, this is all you need to do is this right here. Yeah, and then, by the way, let me go down here momentarily. Yeah, so now this one here actually is a linear transformation. So for this one, you're going to have to write out all the details, the ax plus by, et cetera.
Yeah,
right? And this one also, but this one fails, that one fails, and this one fails. All these last three, you're just going to find counterexamples, which you can, again, pretty much just randomly choose vectors and show that they don't work for those random vectors. Okay, let me stop the recording here.